let's have a look at this question. So here we are given a balanced reaction, right? And we have to find out which one is the oxidant and which one is the reductant, right? So what is an oxidant? Well, it's a molecule or a compound which itself gets reduced but oxidizes the other, right? And what is a reductant? Well, it itself gets oxidizes but reduces the other. Okay, so what's the approach to this question? Well, you'll need to find out the oxidation states of the elements, right? To check which one is getting oxidized, which one is getting reduced, and through that we'll know our oxidant and reductant in this question, okay, for this reaction. Okay, let's have a look, or I would say, okay, so let me write this reaction once. So this is 3Na2HASO3 plus KBrO3 plus HCl, 6HCl giving 6NaCl plus KBr, 6NaCl plus KBr plus 3H3ASO4. Right, so what do we know here? We know sodium will exist in +1 state, oxygen will exist in -2 state, right? So what do? We need to find out the oxidation state, or actually the oxidation state. Oh yes, right. Okay, so let's check it out. So sodium will be +1, right? There are 2 atoms, and then we have +1 for hydrogen, plus X for AS, and oxygen. We have 3 atoms and each one has -2, right? And the whole molecule is 0, hence it's 0, right? So this comes out to be 3 minus 6 plus X is equal to 0. So X comes out to be +3, okay? So AS is in the +3 oxidation state. What about KBrO3? Let's have a look at that. Okay, so KBrO3. Okay, so here potassium will be in +1 oxidation state. Bromine has X, right? We have 3 oxygen atoms, -2, where this will be equal to 0. So X comes out to be +5. So in KBrO3, bromine is in +5 oxidation state. Okay. Okay, so what about bromine atom in KBr? We know that potassium will be +1, so bromine comes out to be -1 oxidation state, right? What about H3ASO4? Let's check it out. So we have H3ASO4, right? So this will be 3 into +1. Hydrogen is in +1. X is the AS, right? Plus 4 oxygen, -2 each carbon, and this is 0. So -2 for each oxygen atom. So this comes out to be 3 minus 8 plus X is equal to 0. So X comes out to be +5. Okay. So here we know that AS is in +5, right? So let's find out the reduction halves and the oxidation halves, right? So we can say that Na2HASO3 is going to H3ASO4, right? I'm not writing the stoichiometric coefficients here, just seeing the, the change in the oxidation state. So here in the reactant side, it's in +3. And in the oxidation, in the product side, it is +5. So what has happened is it has lost 2 electrons, right? It itself is being what? It's itself being oxidized. It is itself being oxidized. Okay, what about KBrO3? Okay, so we have the other half is KBrO3 going to KBr. So here the oxidation state was +5, right? And it is going to -1. So it has what? It has accepted, or it has gained 6 electrons, right? And here it has lost 2 electrons. So here it is being reduced, right? So what did we say? The oxidant is something which itself gets reduced but oxidizes other, right? So what would be the oxidant here? It will be KBrO3, right? Because it's itself is being reduced. It's itself being reduced. Why? Because potassium is same. It's +1. Oxygen is same. It's -2. But the bromine atom, the oxidation state of bromine atom is changing and it's getting reduced. Hence, it is the oxidant. What about the reductant? So reductant, it reduces other but itself gets oxidized, and we know that is what? That is Na2HASO3, right? Oxidation of state of sodium and oxygen are same. It's +1 and -2, and hydrogen is also same, it's +1, and the AS is changing from +3 to +5, accepting 2 electrons, and hence it's getting reduced, and that's why it's the reductant, right? Okay, let's check which option does it match. Oxidant is KBrO3 and reductant is Na2HASO3. Okay, so we can check here. We know here what the KBrO3 is, what is our oxidant, and Na2HASO3 is our reductant. So the correct option to this question is option B. Let's have a look at this question. So here we are given 4 compounds in front of us, and we have to find the correct order of their resonance energy, right? So let's have a look at these compounds one by one, right? So the first one is pyrrole, right? So what happens here is that the lone pair of nitrogen is delocalized over the whole molecule, right? So this means how many electrons are being delocalized? The 4 pi electrons from the double bond and the lone pair of nitrogen as well, right? So this comes out to be 6 pi electrons, and this molecule is cyclic as well, and this is planar as well. Why planar? Well, the lone pair of nitrogen, they are being delocalized over pure p orbitals, and this nitrogen is making what? It's making 3 sigma bonds, so it is sp2 hybridized. Similarly, all other carbon atoms, right, the 4 other carbon atoms are also making 3 sigma bonds. They are also sp2 hybridized, which makes the molecule planar. And 6 pi electrons, the 6 pi electrons being delocalized over the molecule, this satisfies our Huckel rule as well, right? So yes, this molecule is aromatic in nature. Okay, now let's have a look at the thiofuran. Actually, it's also the same case. It's pretty similar. So what happens here? The lone pairs are also delocalized, right? The lone pair of sulfur is being delocalized. So that means total pi electrons are what? 6 pi electrons being delocalized over the molecule. It's cyclic and it's planar as well. Why? It's making 3 sigma bonds. It's making 2 sigma bonds. However, the lone pair is in the hybridized orbital, so which makes the hybridization as sp2, right? What about furan? Actually, furan is also pretty much the same, right? So one of the lone pair is being delocalized, so that makes 6 pi electrons, cyclic as well, and it is planar as well. Why? Because the lone pair that is being delocalized in the pure p orbital, and this oxygen is making 2 sigma bonds, and this one lone pair is in hybridized orbital, right? So this is sp2, and other carbon atoms as well are sp2 hybridized, which makes the whole molecular planar, right? So what do we know? We know that out of those 4 molecules, these 3 molecules are aromatic in nature. Let's have a look at the cyclopentadiene, right? So cyclopentadiene is not aromatic in nature. Why? First thing, this carbon is sp3 hybridized, right? Another thing, there are only 4 pi electrons being localized or being delocalized, right? So this is not aromatic, right? So this molecule only has resonance energy. It's not stabilized by aromaticity. Hence, this compound will have the least resonance energy, right? However, these 3 molecules will have more resonance energy as compared to cyclopentadiene, right? Because they are being stabilized by aromaticity. So what do we know? We know that the fourth compound will have least resonance energy, right? What about now these 3? Okay, so when we look at the resonating structures of pyrrole, thiofuran and furan, right, what do we find? We find that nitrogen and sulfur and oxygen, they have positive charge on it. Let's have a look. So I'm drawing one of the resonating structures of pyrrole, thiofuran, right? This will be a positive charge. and the furan as well. Okay, so these are one of the resonating structures of pyrrole, thiofuran and furan. What do we see? We see that the positive charges on nitrogen, sulfur and oxygen, right? Now we know that oxygen is highly electronegative, followed by nitrogen, followed by sulfur, right? And positive charge on electronegative atom is not that stable. So the positive charge on oxygen will not be stable, right? So from this information, what do we know? We know that the sulfur having positive charge would be more stable, right, as compared to nitrogen having positive charge, and the oxygen having positive charge will be least stable, right? So since the more the stable the resonating structures, more will be the resonance energy, right? So looking at this information, what do we know? We know that the second compound will have highest resonance energy. Why? Because it is being stabilized by aromaticity, right? Because of the delocalization of 6 pi electrons and being following all the 3 criteria for a compound to be aromatic. Also, the positive charge on sulfur is less stable as compared to positive charge on nitrogen and oxygen, right? So second compound will have highest resonance energy, followed by first, followed by third, and the least one we already know is fourth. Right. So this is the order of the resonance energy of these 4 compounds. Let's have a look. Which option does it match? 2, 1, 3, 4. Well, it matches our option D, which is the correct option. Let's have a look at this question. So here we have to find out the URMS of oxygen, and the pressure is given to us as 1 into 10 to the power 4 Pascal. And the density of oxygen gas is given to us as 1.5 kilogram per meter cube, right? And we have to find the URMS in meter per second. By looking at the options, we can clearly say that. Okay, so what do we know about URMS? We know the formula is under root of 3RT by M, right? We also know that PV is equal to nRT. So PV by N becomes RT. So we can displace this value of RT in our equation 1. So this comes out to be under root 3 PV upon NM, right? And what is N? N is number of moles, which is given by given weight upon molar mass, right? So I'll substitute that as well. Okay, so I'm just writing here N is what? Given weight divided by molar mass. So this becomes 3 PV upon given weight into molar mass is already there, and the molar mass in denominator will go to the numerator, right? Molar mass cancels out. What do we have here? We have 3 PV by W, right? And what do we know here? We know that the given weight upon volume, right? This is what? This is density. So this comes out to be under root 3 P upon D, right? Where D is the density. And the pressure value and the density value is already given to us. Pretty easy, right? So under root 3 into 10 raised to the power 4 divided by 1.5, right? So one thing you have to ensure here, right? Here we are pretty lucky that the units given to us were exactly the ones that we wanted. Why? Okay, let's have a look here. So pressure is given to us in pascals, right? What is 1 Pascal? That is kg per meter second per second square, right? And here the density given to us is in kg per meter cube. Kg per meter cube, right? So here if you see kg cancels out, right? And this comes out to be what? 3 into 10 raised to the power 4 upon 1.5. This comes out to be second per square, like second raised to the power minus 2 and meter raised to the power minus 2, right? And if you bring it out of the under root, this becomes what? This actually becomes second minus an inverse and meter inverse. So this is 3 into 10 raised to the power 4 upon 1.5 meter per second. That's what we wanted, right? So here the units were pretty straightforward, given to you correctly, but you have to ensure that when you're solving these questions like this, always ensure that your units are correct, right? You can get the velocity or the URMS in meter per second only when your pressure is given in pascals and the density is given in kg per meter cube, right? The SI units. Okay. Okay, so let's solve this question now, right? So this is 2, right? So under root 2 into 10 raised power 2, right? Under root 2 is what? 1.41, right? Into 10 raised power 2. So I've just written an approximate value. So this almost comes out to be 141 meter per second. Let's check which option does it match. Well, it matches our option C, which is the correct option. Let's have a look at this question. So here we are asked that if we treat vicinal dihalides with alcoholic KOH, what type of reaction is it, right? So let's have a look at one such reaction, right? So we have CH2, and we have Br over here and Br over here. So this is an example of vicinal dihalide, and we are adding alcoholic KOH. So what happens if we have alcoholic KOH? Well, dehydrohalogenation takes place, right? So one of the H and one of the Br will be removed. So one of the H and one of the Br gets removed, right? And what do we get? We get CH2 double bond CHBr, right? So this is what? This is alkynyl halide, right? This is ethynyl halide, and that's all. If you even add alcoholic KOH, you're not going to get alkyne. So if you want to get alkyne, what happens? What would you need to do? You need to add NaNH2, that is sodamide, right? So NaNH2 exists as Na plus NH2 minus, right? So this NH2 minus, it will try to abstract this proton, right? And the carbon will try to make a triple bond out of those 2 electrons left by the hydrogen, right? And bromine atom will leave as Br minus. And what do we get? We get CH triple bond CH, right? However, the question that was asked was, if we have vicinal halide, and if what type of reaction would it be when you add alcoholic KOH? Well, if you add alcoholic KOH, the dehydrohalogenation takes place, right? The HBr leaves, and what you're left with is alkynyl halide, right? So the correct option is option A. Let's have a look at this question. Here we want to make acetylene by adding water. And we need to know to which compound, to which substance should we add water so as to get acetylene. So what is acetylene? That is CH triple bond CH, right? So this is a very, very important reaction, right? So if you have calcium carbide, if you add water to it, right, what do you get? You get ethyne plus calcium hydroxide. Right, so this is a reaction, very, very important. You should know it, you should learn it, right? Just learn it by heart. So let's see, how do we get calcium carbide, right? So we have calcium carbonate, right? We heat it and we get calcium oxide plus carbonate plus carbon dioxide, which is released, right? So if on calcium oxide, if you add carbon, that is coke, right? Not the coke, carbon coke, right? If you add it, what do you get is calcium carbide, right? So what is carbide? C triple bond C, right? That is carbide. And calcium we know is in +2 oxidation state, right? So here we have negative charge on both the carbon atoms, right? And when you add water to this calcium carbide, right, what do you get? So the calcium, so from the water, right, the H is replaced here. Calcium is replaced by proton, right? And we get calcium hydroxide, right? So if you want to get acetylene, that is ethyne, by adding water, what should you add water on? You should add water on calcium carbide. So the correct option here is option B.